All right, now that we're back from solving for QC, and we found that it's basically 50 million BTUs per year, does that help us solve this equation? And the question is, what equation are we trying to solve for? Remember, we're trying to find the work of this compressor. And so I'm going to go back to the other videos. Remember where we put a system boundary around the compressor. We actually did it around each component. And we performed an energy balance around that system. Remember, this was system 3 from the video. So system 3, remember our energy balance was the work of the compressor equals the mass of the refrigerant times the enthalpy at state 3 minus the enthalpy at state 2. So now we have an equation. If we could solve this equation, we can find the work it's going to take to drive this compressor. So do we know H2? Do we know H3? Answer to both of those, at least right now, is no. Do we know the mass of the refrigerant that we need? Again, the answer to that right now is no. The question is, how do we find H2, H3, and the mass of the refrigerant with the information that we have? Well, we're going to have to constrain the system a little more. And I kind of talked about this in the second video on this topic, where I talked about the temperature here needing to be around the temperature of the reactor. If you don't remember that, let's talk about it now. What's this refrigeration cycle trying to do? Remember, we've got two sides. Split it down the middle. Cold side, hot side. Our big picture idea that we're trying to do with this system is take energy from the cold side and dispel that energy to the hot side. Now, once we start talking about heat transfer, we'll know that heat is transferred across a temperature difference. So we need a temperature difference between this exchanger and whatever it's exchanging energy with, which is our reactor, and also this exchanger here with whatever it's exchanging energy with, which is going to be, in our case, the atmosphere. There needs to be a temperature difference between the atmosphere and the working fluid here. There needs to be a temperature difference between the reactor fluid and the working fluid in the refrigeration cycle. Now you'll get to a class where you'll detail this out. Ideally, it will probably be heat and mass transfer. For right now, what we're going to assume is that we need a 7-degree Fahrenheit temperature difference on both sides in order to effectively have good heat transfer. So let me write that out. I'm going to write any other assumptions that I'm going to propose over here. And I'm assuming that the delta T, or the temperature difference, needs to be equal to 7 degrees Fahrenheit. Now this delta T, again, is representing the temperature difference between the working refrigerant and whatever it's exchanging energy with. In this case, it's the reactor contents. In this case over here, we have the refrigerant and the atmospheric air. So we want a 7-degree temperature difference. So we know what our reactor needs to run at. Our reactor needs to run at 40 degrees Fahrenheit. So if we want to know the temperature that this cold side has to be at, because remember, if I know the temperature at any point here, it's the temperature across the whole thing due to our isobaric assumption for the ideal case. Also given that it's in vapor-liquid equilibrium the whole time, which is also an assumption that we made on the ideal case. So, what's going to be the temperature over here? So remember, T1 equals T2. And we want to know what that is, but that's also going to equal the reactor temperature, 40 degrees Fahrenheit. Now remember, since this is the cold side of the refrigeration system, this has to be colder than the reactor in order for the reactor heat to dispel into the refrigeration fluid. So it needs to be 40 minus 7, which will give us 33 degrees Fahrenheit. So now let's come in here and fill out some information. Now remember what I told you, that once we constrain one of these state properties, we have the rest of them. So if we were to go and look up in R134A, if you look at the other video where I do this, if we were to go look up R134A and we put in a temperature, we have all the other values for pressure, entropy, and enthalpy. I'm just going to write those out, but you can look those up. This table that I'm talking about is going to be equivalent to the steam tables, okay? But it's going to be the steam tables for R134A. Those steam tables are just the saturation tables for water, okay? We're looking at the saturation table in this case for R134A. So the pressure here, again the pressures will be equal, it's going to be 43 psi A. Same value here, 43 psi A. The enthalpy here is 172 BTUs per pound. And I put roughly in my notes probably because I rounded that. Okay. Let's see here. What are our entropy values? Our entropy here is 0.4127. Units here are BTUs per pound degree Rankine. Okay. Now, entropy here is not the same as entropy here. We can infer that because here we have vapor plus liquid and here we have saturated vapor. Entropy's gone up. So you can fill out the rest of this information, however, given your steam tables, so to speak. You will have a different enthalpy for this because it's partial vapor, partial liquid, and you'll have a different entropy. These two will be difficult to find unless you know the percentages of vapor and the percentages of liquid. That's the reason I left them blank. But good for us, at least for our case, they don't wind up being important. Now, what's the next thing that we need to look at here? What do we have? Can we solve anything? We just went through this whole exercise. We got all of our information on this side. Does that help us over here at all? Well, we found one value. We've got our H2 now. 172 BTUs per pound. Do we have H3? can we find H3? H3 is right here. Superheated vapor. Do we know any of these values? We know one of them because of the simplifying assumption we made. What did we say? S3 is equal to S2. Therefore, S3 okay. I'm going to erase this. It's getting in the way. And I'll just write the value for QC right here. Remember, it was 50 million BTUs per year. Okay. Now, does that help us? Can we now solve for H3? Remember, what did I tell you over here? If you knew one of the state functions, you could figure out the other one. Can you do that here? The answer is no. It's important you understand why. We're not in vapor-liquid equilibrium anymore. The superheated vapor. So I've got to constrain two things. Because it's a pure substance, I've got to constrain two things now. Do I have something else to constrain? Well, what did we talk about over here? Remember, we talked about we need heat transfer to happen, and we know what we're transferring the heat with. And we're going to dispel this to the atmosphere, to the air. Okay, I didn't tell you that in the problem, but these are some of the things that I want you to think about, to be able to assume and infer on your own. Now, maybe you would dispel that to another liquid, but most commonly you're going to dispel this to the atmosphere with a fan, a fin fan. So just like we did over here, we knew the temperature of the reactor, what it was taking heat out of. So here we need to know the temperature of the ambient air. And we could go out and take a thermometer and measure the temperature of the ambient air. But I would caution you in doing that, because you need this refrigeration system to work at all conditions. And so what is going to be the worst condition that it's going to work at? When the ambient air is the hottest. Okay? When the ambient air is the hottest, this refrigeration system is going to be under the most stress. If you size it for a cooler temperature, you're not going to achieve that your needed BTUs over here, because it can't dispel enough heat on this side, because you didn't give it, once you get into exchanger design, you probably didn't give it enough surface area. But for right now, just know that you want to size this for worst case scenario. And so let's say we're down in the Gulf Coast where we're at. It's going to get up 105, 110 on a bad day. You need it to work on the bad day. So we're just going to go worst case scenario and say the temperature on this side of the exchanger, on the air side, is 110. So if we take our assumption over here, and we plug that in, that means that our refrigerant needs to maintain at 107, it needs to be at 117 degrees or hotter in order to effectively have good heat transfer. Okay? So which one of these temperatures is going to need to be set at 117? T3 or T4? It's T4. Okay? And the reason that is T3 is going to be hotter as it cools down. It's superheated vapor. It's going to cool down to its its saturation point to saturated vapor, and most of the heat that's being removed here is latent heat. It's not sensible heat. And so your latent heat transfer, where you're going from a vapor to a liquid, is going to be your biggest load. So you're going to want to size it for your latent heat regime, which is going to be this T4. Because remember, once it hits vapor-liquid equilibrium, the temperature at which it's condensing then is going to be equal to T4. So we want to say T4 needs to be at 117 degrees, well, or hotter, but we're using a 7-degree temperature difference. I'll show you how I get there. T4 needs to equal the ambient air, which we assumed it's 110 degrees Fahrenheit on a bad day. And remember, because here the fluid is dispelling heat to the environment, which means that the fluid, the refrigeration fluid here, needs to be hotter. It needs to be the hotter substance. So if the outside air is 110 and we want a 10-degree difference, we need to add 7 degrees, and that's how we got our 117 that I just rattled off earlier but didn't show you how. Okay? So how in the world does this help us do anything? Because I just found a temperature that's up here. It has nothing to do with what I'm trying to solve for. In fact, it does. Because what's the assumption we made from 3 to 4? We assumed it's isobaric. The pressures are equal. Since this is saturated liquid, I know the temperature, which also means I know the pressure. So let me look in my notes real quick. So if we were to look up R134A saturation, saturated liquid, basically steam tables, look at 117 degrees Fahrenheit, what we would find is the corresponding pressure is 178 psia. So that means P3 here is 178 psia. Now notice, I've just constrained two of the state functions, which means what? I can find the other one. Okay? So if I go find a vapor that's got a pressure of 178 degrees, or excuse me, 170 psia, and the entropy is this value, I can find the enthalpy. And if we go look that up, the enthalpy value is roughly, I'm putting roughly because I probably round it here, 184 BTUs per pound. It's going to be a specific enthalpy, but nonetheless, it works. It's going to fit right into our equation. So now, we're one step closer to finding the work of the compressor. We know H2, we know H3. We still do not know the mass of the refrigerant. Okay? But we can find the mass of the refrigerant because we know some other things, right? The whole point of us going through this system balance, energy balance, was not for nothing. If we were to draw another system balance, again around our condenser here, remember we called this system 2. I'll write out the energy balance for system number 2. Remember we said that QC is equal to M H2 minus H1. we know H2. But remember, because this is partial vapor, partial liquid, and we don't know the fraction of each, we can't know H1. So are we stuck? The answer is no, although it becomes more complex now. We do another system balance, go back and refer to around system 1. Remember our system 1 balance. What did it say? Remember, it said that H1 is equal to H4. If we plug this value now into into the equation for system 2, right here, so if we say the value for H1 is now H4, rewrite our equation. Can we solve that now? Do we have enough information? Or do we have one unknown? We know H2, we know QC, we don't know M, but do we know H4 even though I didn't write it on the board? The answer is yes. It's a completely saturated liquid. We know it's 100% liquid, so we should be able to go find from our steam tables the value of H4. And in fact, the value of H4, I'm running into my diagram here, but it is 115 BTUs per pound. Now it's getting kind of messy. Again, I just found this along with the other information from the steam table, from the refrigeration steam tables. There's also an entropy value there, but we don't really need it. So again, we know H2, we know H4, we know QC. We can solve for M. Let me just rewrite this equation. I'm going to say M equals QC over H2 minus H4. I put in my value for QC, which is 50 million BTUs per year. My value for H2 is 172 BTUs per pound minus my H4 value, which is 115 BTUs per pound. Make sure my units are lining up. What I wind up with is roughly, I'm just rounding up here, is 878,000 pounds per year of refrigerant. So let's kind of walk through that again. What did I do? Remember, we're looking for the work of the compressor. We found H3, H2, but we didn't know M. We started doing system balances. Could find the mass we thought from this equation because we knew QC, we knew H2, but we didn't know H1. Remember, because we have vapor to liquid. However, we can relate H1 and H4 through the system 1 energy balance. H1 equals H4. Remember, this is from the proof of this is from one of the last videos. Plugging that back in allowed us to find the mass of the refrigerant. So what do we need to do now? Take this back in, plug it in, and solve for WC. So if we do that, our mass is 878 pounds per year. This is going to be times H3, which is 184 BTUs per pound, minus H2, which is 172 BTUs per pound, which winds up being roughly 10,536,000 BTUs per year. So we found the energy requirement for our compressor. All that work for that. But that's how you have to approach some of these problems. Notice the amount of understanding that I had to have, not only of the refrigeration system, the assumptions we made, but also of all the other things that the refrigeration system is interacting with, such as what's my QC value, such as what's my ambient air temperature. And notice I used to not like when people told me this, but you need to be comfortable making assumptions. But you only get comfortable making assumptions when you understand what's going on. And so you need to begin to understand fundamentally what's happening before you start taking off and just doing these equations, filling in numbers blindly. You're going to get to a point eventually where you don't know what you're doing. Now the last part of this problem we'll come back in the next video and do is we need to take this BTU value and convert it to a dollar value. And I'll show you how to do that when we come back. Thank you.